Hello, 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 everybody out there in Calc BC land. Welcome back to another video. We're going to talk about the interval of convergence today. And we've really done well with the Taylor series. You could make the argument that we've certainly dominated that topic the last couple of days, and we're ready to move on and progress to this next new topic. And we've already flirted with it a little bit. In fact, we're going to say there's two types of game plans we're going to have. One being if we are dealing with a geometric power series like we did a week ago. We already talked about interval convergence there. We said, you know what, all we're going to do is we're going to grab our R value and we're going to say as long as the absolute value of R is less than 1, we're guaranteed to have a convergent series. And then we stretched that out and turned it into a compound inequality and wrote it like this, and we created that interval. Today we're going to look at how do we determine what the interval of convergence is for all other types of power series, specifically a Taylor series. And what we're going to do in that case is whenever they ask us for the interval of convergence, we're going to instantly jump to a good friend of ours called the ratio test. And we really did well with the ratio test just before Christmas, and so I think it's going to be a welcome return to a test that we really felt comfortable with. Basically the interval of convergence in a nutshell is asking us for what values of x does our power series converge to the same value as f of x. In other words, let's try to paint this picture here. Generally, we've said f of x is equal to a summation and infinite series. We will say maybe a sub n is my coefficient, and then x minus c to the nth power is the rest of the series. And this particular series is centered at c. And basically we're saying, okay, if I substituted maybe a 2 in for this x value right there, will I get the same answer as if I substituted the 2 in for this x value over here on this side? And that's basically our end goal, is we want to get the same output for the same input. And we want these rascals here to be perfect matches. That's our goal. One of the words that we're going to use to describe interval of convergence, and I think this is fair game to make this conclusion, is that the interval of convergence is another way of saying the domain of a given series. Okay? Think of interval of convergence as domain, and I think we'll all be on the same page. The first question we want to address is, why is every series that God's ever created guaranteed to at least at a bare minimum converge at its center? Okay, and this is going to turn out to be true. So I can tell you right now, every single series that's ever been created is guaranteed to converge at least at its center. And I'm going to prove that to you here really quick here. Let's take a look at the generic form. Okay, this is what a very generic basic series looks like. If we substitute, okay, a c in for x, take a look at what happens. We get a sub n, and then we just get c minus c, which is 0 to the nth power. And if you substitute a 0, you get a sub n times 1 plus a sub, that should be a sub 0, I'm sorry. Then a sub 1 times 0 plus a sub 2 times 0, and then so forth and so forth. Everything after that turns to zeros, and so you end up getting a sub 0 for your final answer, which is a finite number. And so we've just proven that every single series is at least guaranteed to converge at its center. Obviously, though, we're very idealistic and optimistic, and we're hoping that the series converges for many, many more values beyond just its center. A series that converges at its center only is not a very helpful or useful series. Okay, now the domain of a power series has only 3 basic outcomes. That's the great news. There's only 3 possible answers that you could possibly have when you do this. And just as a side note, usually I would say there's probably a 90% chance that when we open up our free response booklet on May 8th, that we're going to have a question on that free response section related to interval convergence. And typically it is about 4 or 5 points out of the total 9 points on that question. So that just tells you how important this topic is and how much of an emphasis the College Board chooses to put on this topic. But basically, outcome number 1 that you could possibly have is what we call convergence at a single point, aka the center only. Like we said, that's not very ideal, that's not our hope, but sometimes there are series that converge only at its center and nothing else. So on a number line, we're visualizing something like this. Okay, let's say it's centered at C, and it only converges at C, and that's it, no place else. All right, outcome number 2, we're going to say that it converges on an interval centered at C. Okay, converges on an interval centered at C. So visually, it may look like this. So we say there's C. This number line that I'm writing down, I probably should have described that a little better, but it's just the number line representing all values of x, and we're trying to paint a picture of which values of x the series converges for. And so as far as the interval goes, it may converge, from maybe, negative a to positive a, where those are centered not around 0, but centered around the center, whatever that happens to be. Maybe 0, may not be. And the distance from the center out to that outer edge is called the radius of convergence. That's a new term we're going to incorporate quite a bit, the radius of convergence. Okay? And a lot of times, we're just going to use the capital letter R, but that just describes the length from the center to the outer edge of that interval. And outcome number 3, we're going to have to slide down here just a whisker, is the best case scenario. Every time we go into a new series, this is what we're hoping for, and we'll say it converges over the entire real number line. Okay, the entire, I should probably start that word with the E. Leave it to me. Me and my spelling are not the greatest. I think back in middle school when I was in, or no, when did we do spelling bee? Maybe back in 6th grade or something like that. I think I was eliminated in the second round. I didn't last real long that day, unfortunately. But anyway, it converges over the entire real number line, and if we paint a picture graphically here and we represent all values of x and it's centered at C, we're going to get a series that converges for every single value of x. It doesn't matter what you plug in for x, you can plug it into the series and get the exact same sum or output that you would as if you plugged that value of x into the original function f of x, and this is our best case scenario. Now in this particular case, we would say that our radius of convergence is actually equal to infinity because the distance from the center to the outer edge of this so-called interval is infinity. And if we back up, let's go back to that first example. What would you say is the interval or the radius of convergence for this first one? I would say that the radius of convergence is 0 because the distance from the center to the outer edge is non-existent. It's just 0. So there's 3 possible outcomes. Those are what they look like graphically, and we'll start to look at those in some specific examples. We're going to talk about our game plan. It's kind of a 3-step game plan today, and it may not make a ton of sense until we apply this game plan to a few examples, and you'll start to get the hang of things and get comfortable. But they're essentially going to ask me for the interval of convergence. So here's step 1. We're going to use the ratio test. Okay, and don't worry, we're going to review that. We're going to talk about some of the specifics of the ratio test, but it'll come back quick. It's kind of like riding a bike. But we're going to use that ratio test to determine what the I'll squeeze an M in there. Determine what the radius of convergence is. Then once we find the radius of convergence, step number 2, we're going to say we're going to use that radius of convergence to then determine the interval of convergence. And then last but not least, and this is the one that's going to make no sense right now when I say it, but it'll make a lot of sense hopefully 5 minutes from now, is we need to then test, or maybe another word I could say is check, each endpoint individually. Okay, and that's a step right there that usually costs a lot of people, not from Hamburg anyway, but they'll cost other people points on the AP exam. But we're going to check each endpoint individually to see if we converge at those endpoints. Specifically, do you remember outcome number 2 that we just talked about in the last slide? And I put kind of those parentheses there to represent the interval. Those parentheses could turn into square brackets, and instead of an open interval, we could have a closed interval. In fact, it could be open on the left edge and closed on the right edge, or vice versa. These endpoints are going to be rather tricky. So right now I want to take a few seconds to jump in our time machine and go back to early December when we talked about the ratio test for the first time. And basically the ratio test says you're going to evaluate a limit as n approaches infinity, and it's going to be the absolute value of the n plus first term divided by the nth term itself. And after we get done evaluating that limit, we're going to say that our answer is L. And then there's 3 possible outcomes. If L was smaller than 1, the series definitely converges. If L was bigger than 1, then the series definitely diverged. And then there was that rare case where we said if L is equal to 1, then we're really not sure. It's inconclusive. In other words, the series may still diverge or converge at that point. We would just then have to choose another test in order to figure that out. Okay, we're finally ready to dive into an example. We've got 3 examples on tap here to put in our notebook, hopefully one that's going to exemplify each of the 3 outcomes. And our question for all 3 of these is going to be the same. They're going to ask us to find the interval of convergence. And number 1, certainly no easier than the other 2. We're going to jump right into it and get after it. But here's what the original series looks like. It's an alternating series. And right here, you can tell that the series is centered at -1. So if nothing else, we know it's going to converge at -1, and we're hoping for more than that. We're a little greedier than that. Step number 1 in our game plan said that we're going to jump right in and use the ratio test. And so here's what the ratio test looks like. We're going to ask ourselves what's happening as n approaches infinity, as n gets huge. And basically what we have is I'm going to disregard the -1 to the nth power because the absolute values there are there to kind of soak that up and evaporate it. But then we have x plus 1 raised to the n plus 1 power all over 2 to the n plus 1 power. Notice we're just substituting the n plus 1 in for the n's. Now, instead of dividing by the nth term, I'm going to actually multiply by the reciprocal of the nth term. So I get something like this, and we're going to clean this up a little bit. The key here that I want you to focus on is it's the limit as n approaches infinity, not x. Okay, we really don't care what's happening to x. As we do a little bit of canceling here, we could get just x plus 1 to the nth power on top, and then on the bottom we'll cancel those rascals and get just 2 to the first power on the bottom. And here's the trick. If this is the limit as x approaches infinity, it'd be a totally different ballgame, and I would call it large over small, all right? But it's not. It's the limit as n approaches infinity, okay? We're asking ourselves, what happens as n gets huge? Well, you'll notice there are no n's in here. All right, so basically what we're going to say is the answer to this question, once we evaluated it, we got an answer of x plus 1 over 2. And this right here represents the L value that I had on the last screen as regards to, what's the answer to your limit, basically. Now, in order for this rascal to converge, okay, we said just moments ago, we said that we wanted L to be less than 1. And so I'm going to say, well, my x plus 1 over 2, we'll throw those absolute values in there, has to be less than 1. In other words, -1's less than x plus 1 over 2 less than 1. We're going to multiply everybody by 2. And then the last thing I'm going to do is I'm going to subtract 1 from everything. And we got -3 is less than x, which is less than 1. And of course, like we mentioned earlier, this whole thing's centered at -1. We knew that right from the beginning looking at the original series. And just to kind of paint a picture visually on the number line, we said if this number line represents all values of x and we're centered at -1, then our interval is going to extend from -3 all the way up to +1. Now the trick becomes, what we don't know is, does it converge at these endpoints, okay? In other words, is it going to be an open interval or is it going to be a closed interval? We might be closed on the left, open on the right, vice versa. So what we're going to do now is, we know that our radius of convergence, we already know that the radius right here has a length of 2. That's our radius. Now I need to investigate and see what the actual interval is going to be. In other words, I need to test the endpoints. Here's where it gets real exciting. I'm going to start off with the left endpoint, okay? So let's check the left endpoint. And this will go much quicker once you get a little practice under your belt. I'm going extremely slow right now. The left endpoint was x equals -3. So I'm going to substitute the -3 into the original series. Go way back to the beginning. We're going to substitute that -3 in for the x. Okay, we'll clean this up just a whisker. We got -1 to the nth power, and then we got -2 to the nth power, all over 2 to the n. If you multiply your two terms on top, you multiply these two numerator terms together, you're going to get 2 to the n. And then you'll notice that just turns out to be 1. And the summation of 1, it's almost so simple, it's weird and hard. But you'll notice if you said, okay, If you expanded this out, it'd be 1 plus 1 plus 1 plus 1 forever, and the sum would then diverge. And so we would say that the left endpoint is not convergent, it's divergent because of that infinity sign right there. And now I'm going to check the other endpoint, the right-handed endpoint, which I believe was a positive 1. So the right endpoint was x equals positive 1. Substituting it into the original. Let's see, did I say that right? Yep, okay. We'll clean it up just a whisker, and we got negative 1 to the nth power, 2 to the nth power over 2 to the nth power. You'll notice that these bears cancel, and we end up with negative 1 to the nth power. Now this one's kind of weird, okay? If you started to expand this one out, your first term would be a 1, and then you'd add a negative 1, and then you'd add a 1, and then you'd add a negative 1, and then you'd add a 1, and the question becomes, does this one converge? Well, what's happening is, if you consider your sequence of partial sums, your sum oscillates from between 1 and then 0 and then 1 and then 0 and then 1 and then 0, etc., etc. And so we're saying, well, we're not, the sum's not diverging towards infinity, but it is diverging because it's not approaching one single finite conclusive number. So again, we'd say that this endpoint also diverges, and therefore our interval of convergence is going to be open bracket negative 3 comma 1 open parenthesis again. There's your interval of convergence, ladies and gentlemen. Little lengthy this time, but we'll get quicker at them. Okay, here's example number 2. Looks very nice and innocent. I'm going to jump right into my ratio test here, and I'm going to have, I'm going to write the n plus first term. Notice the n plus 1 goes in parentheses with the squared on the outside right there. Then we're going to multiply it by the reciprocal of the nth term, which was the one that was given to us at the beginning. Now we're going to try to clean this up a little bit, and there's not actually a whole lot we can do. If I cancel these two terms, I get just an x to the first power on top, but then I can't really cancel the polynomials, and I just get x times n squared all over the quantity n plus 1 squared. And foiling that one out really doesn't help us. Now I didn't do this next trick on the last problem, but what I like to do is I'd like to kind of pull the x out in front. And so what I'm going to do is I'm going to factor out the x, and it has the absolute values actually have to stay on there. And I'm just going to ask myself, then I'm just going to leave everything else the same. Now the reason that's legal is because the limit is asking, what happens when n gets huge. It's not worried about x, so x is basically, irrelevant, and you could pull it out front. And that's something that I strongly recommend that you do. Now you can put all of your energy onto this part right here and not be distracted by the x's, okay, which is easy to do. And as you evaluate that limit, you'll say, well, that's just same over same. And as far as comparing the degree of the numerator to the degree of the denominator, and you get a value of 1. And then if you multiply that by the absolute value of x that we just pulled out, we could then say that the answer to this entire problem is the absolute value of x. Or in other words, that right here is what I would consider the L that we get from evaluating the limit. So next, the interval of convergence is going to be, we'll say, whenever the absolute value of that x value is less than 1, we're going to get a convergence series. So as a compound inequality, it looks like this. It's centered at 0, and you could have decided that right at the beginning when you looked at the original problem. Probably should have made a note of that right at the beginning just to remind ourselves. And now the only thing left to do is to test those endpoints. So I'm going to go ahead and check the left endpoint. I'm going to substitute a negative 1 back into the original series. And let's see, what did that look like? Let's go series. We've got a negative 1 to the nth power all over n squared. And you'll notice this is an alternating series. So I'm going to use what's called the alternating series test. Remember those days? We're going way back before Christmas. And basically we would say the limit as n approaches infinity of 1 over n squared. That does approach 0, which then guarantees that this one does converge. That's kind of exciting. We haven't seen that yet. If I check the right-handed endpoint, all right, we're going to go ahead and we'll substitute a positive 1. Positive 1 to the nth is just 1 all over n squared. Now this is a p series, p-value of 2, which is greater than 1, therefore this one also converges. So here's an example of both endpoints converging, and when I'm all said and done, I'm going to say that the interval of convergence is -1 to +1. Both endpoints are included. We say that this is an inclusive interval, and that's my answer. All right, we're coming down the home stretch, and we're on to number 3, and this is going to be the most exciting one that we do by far. The outcome is going to be rather bizarre, and we're going to try to sort it out and interpret it. Now, as we get ready to use that ratio test, I want to remind you that we are substituting an n plus 1 in for just the n, okay, like right there, right there. And then what we do is we substitute the n plus 1, and then you distribute the 2, and then you add that 1 that's dangling at the end. And that's how we're going to set up our ratio test and try to represent the nth plus first term. So limit as n approaches infinity. It's now going to be x to the 2n plus 3 power all over the quantity 2n plus 3 factorial. By the time I distribute the 2 and combine all my like terms, multiplied by, let's see, 2n plus 1 factorial all over x to the 2n plus 1 power. And this is kind of an interesting one. We're going to try to sort things out here. If I canceled those two terms, what would you be left with? Ask yourself that. What would we be left with? If I subtract those exponents, I get x squared, and that's it. And then if I expanded out these factorials and canceled them, let's see, I would be left with, I'd still have a 2n plus 3, I'd still have a 2n plus 2, but, whoops, that's a 2. But then every term below that would cancel out perfectly and evenly, and this is all I would have. Now take advantage of that trick I used on the last example where you factor out, essentially, any term that possesses an x. And so I factored out the x squared, and believe it or not, the absolute values are now irrelevant because of the squared, so I don't even have to waste my time writing those absolute values, but I do need them here. 1 over the quantity 2n plus 3 times the quantity 2n plus 2. You could FOIL them out, but that's unnecessary. Now evaluate this particular limit. The last limit we did turned out to be a 1. But this limit, which you'll notice, the power phi is small over large, okay? So this limit right here has a value of 0. And then you could bring down your x squared term. You multiply those two guys together, you get an answer of 0. So your first instinct may be to think that that's a bad thing. But this is actually a great outcome, okay? We can celebrate this outcome. We love this outcome because what that means, okay, think about what this means. It means regardless of what you substitute for x, the ratio test is going to yield an answer of 0 every single time. And you know what's beautiful about 0? 0 is less than 1. So that means that this particular series converges for all values of x. We'll put a little exclamation there just to celebrate that fact. All right, I'll say it again. Regardless of what the value of x is, we're going to get an answer of 0 every single time you do the ratio test, and that means it's going to converge for all values of x. This corresponds to the third outcome we discussed at the beginning of the lesson. If we represented this graphically, and we said, all right, this series is centered at 0, and this number line represents all values of x, the series converges from negative infinity all the way to positive infinity. It doesn't matter what x is. You can substitute anything in for x. And you don't even have to worry about checking the endpoints because, well, there are no finite endpoints, all right? So the interval of convergence is simply the interval from negative infinity to infinity. The radius of convergence would be infinity itself. That's the distance from the center to the outer edge. All right, so I hope that answers all your questions. I didn't do an example where it converged only at its center. I thought that one was kind of self-explanatory. You'll probably see that a couple of times in your classwork tomorrow, but I think we'll take care of that when it comes up. So very, very important lesson. A lot of things to think about. I hope we were able to grasp most of them, and anything we didn't get or feel real comfortable with, we'll tackle tomorrow. Have a good night.